So the last time we left after stating this theorem, this is the primeval adjoint functor theorem. Maybe some of you have got some question about the word primeval. Primeval simply means that it came first in the history. Yeah, I mean, what is the simplest possible thing that you can think of? So it starts with this, that okay, if a functor has the property that it preserves all limits which are present in there, then obviously it should have a left adjoint, because we have seen one implication of this, which is very easy, but the second implication is what we are interested in. Okay, so however, for this we have to give up our set theoretic constraints. This theorem states that suppose G from D to C preserves all limits, yeah, I mean not necessarily small limits, then G has a left adjoint. Okay, so then I want to point out your attention to this particular result that we have done. Okay. Do you remember this? So given a functor G, specifying a left adjoint for G is equivalent to specifying an initial object for the arrow category, yeah, where you are talking about each A in object of C. So we want to connect these different things. We are given that it preserves all limits, then we have to somewhere use that all limits means all large limits also if necessary. Well, what can be large? So I am going to write down two lemmas at this point, and those two lemmas together with the statement that I just showed you, that will complete the proof. The first lemma is quite simple. So I am just going to call it lemma 1. It says that suppose A is any category, then A has an initial object if and only if the diagram A to A, identity diagram on A, has a limit. See how beautifully we are making a transition from initial object, which is a co-limit, to a certain diagram having a limit. Moreover, by this particular procedure, we are also saying that A can be any category and the shape of this category can be large, because the shape of the category is A itself. Yeah, in normally wherever we write J, we are writing A, and the functor is identity. Yeah, this is a very simple theorem, a simple lemma to prove. Yeah, what do you do? So suppose A has an initial object, then can you tell me what is the limit cone of this diagram? Suppose A has an initial object I. What is the limit cone over this diagram? Can you tell me? A, identity? No. What do you need to start with? The cone should have a summit. Yeah, that summit has to be one object. Well, you only know one object right now, one special object, namely I. And then you need one morphism for each object of the shape category. Okay, what is the shape category? A. So you need some morphism from I to the identity of the base object. And do you know such object, such morphism? Since I is initial, exactly, there is exactly one. Don't say at least one. Yeah, but at least one will be useful later on as well. Yeah, so then it is easy to check that okay, I'm just going to use this I to A, yeah, and I'm going to write unique A. Yeah, unique A, you understand? It's the unique morphism where A varies in objects of the shape category is a limit cone. For this diagram. Okay, so I'm not going to verify this. I believe by now you are all ready to check this. Okay. For the converse part, yeah, suppose we are talking about this. So suppose B to A, and this is FA, A in objects of A, is a limit cone for the identity diagram on A. Okay, what can we do with this? Then, because it's a cone, what do we know? Something commutes. Yeah, then you start with this B, then for any A to C, F from A to C, we have that the diagram commutes. Which diagram commutes? Well, this particular diagram. This is FA, then this is FC, and this is F. We have this diagram commuting. Okay, so in particular, what can we conclude from here? We have to substitute something very specific. Can you tell me what? I and 1 sub C. Where is I? We have to prove, we are yet to prove that there is an initial object. What's your guess for initial object here? B. Okay, so how will you do that? In particular, which diagram commutes? B to B and then to A. What is the morphism B to B? Well, it's no, FB. See, you just have to substitute in this diagram. This is FA and this is F. Yeah, in particular, this commutes. And for any morphism, it commutes. Yeah, for any A to C. So in particular, I choose this. In particular, this commutes. So therefore, by uniqueness, so I mean, what did we get just now? Maybe I should write one more step in between. Thus, FB is a factorization of the limit through itself. Do you understand this step? So this second B, there is one B at the top, you can imagine, yeah, and one B at the bottom. So the bottom B also forms a cone over your diagram, and the top B also forms a cone. So this FB is a factorization of this cone through itself, limit cone through itself. But we already know one such factorization, namely identity map. Okay, so therefore FB is equal to the identity object on B. Therefore, what do we get now? Moreover, yeah, for any F from A to C, from any F from B to A, we have, what do we have? F composed with, exactly, F composed with identity at B is equal to F sub B, F sub A. Very good. So therefore the size of home set, yeah, size of home set, which I will write as this, from BA is equal to 1 for each A. And this is the proof complete. You understand, this is a very simple proof. Okay, so now what we have shown. So suppose G from D to C preserves all limits which exist in D, then G has a left adjoint. And the earlier statement that we saw, that G has a left adjoint provided every arrow category has got an initial object. So our choice for this calligraphic A category is going to be the arrow category. Okay, we just have to connect these two. So that's our next goal. So now we will talk about lemma 2, and this is perhaps the most important part of the proof. Yeah, there are three versions of the adjoint functor theorem. One is primeval, second one is general adjoint functor theorem, and third one is special adjoint functor theorem. For all three versions, we are going to use this lemma 2, which is the heart of the argument. And then the rest of the argument is always about showing that there is some initial object in an appropriate arrow category. Okay, for the primeval version, we have already done that in lemma 1, and for other adjoint functor theorems also we will do similar things, but we'll have different hypotheses, so different proofs. Lemma 2 is, you can say, that is the heart of the proof. So suppose D has and G from D to C preserves limits of shape J. Then for each A in object of C, the arrow category A arrow G has limits of shape J and the forgetful functor U from A arrow G to what? Can you tell me what should be the codomain of this forgetful functor A arrow G? What are the objects here? Do you remember what the objects are? Morphisms are not the objects, it's a pair, B comma F, where B is in okay, let me write it. B comma F. F is from where to where? Everybody is messing up. Okay, where will I map it to? I will forget about some part. So obviously I should forget about the morphism, because morphism depends on it. And where is B coming from? D. Okay. So the forgetful functor creates them. So actually this statement itself is telling us the way to find these things. Yeah, how do we make sure that A arrow G has limits of shape J? We will create such limits from D. D has limits of shape J, so therefore we will use this forgetful functor to create them. Yeah, I mean, you remember creation has to, like a simple example is always groups. You want to create products in groups. You want to construct products in groups, but then you take two groups and then you forget about their group structure. You only remember their underlying set, and then you take their cross product, which is the product in category of sets, and then you equip that cross product with a group structure. Yeah, so that's how you create them. Okay, so that's what we are supposed to do here. Okay, so what should we start with? We have to start with one diagram in the arrow category of shape J. So let D from J to the arrow category be a diagram. Okay. So now we are going to use some slightly fancy notation. Write D of J, yeah, as, now what is the first component? D of J is always B comma F, but B is the forgetful functor applied to this. So we are going to write U dj comma Fj from A to Gu dj. You understand this? So dj is in fact written using the forgetful functor applied to it. And I mean, for what? For j in object of j. Yeah, dj is just one of these objects. Okay, we are not yet talking about the morphisms. Yeah, these are just objects. So here there is a beautiful connection between cones and morphisms, like cones in category D, cones and morphisms in category, the morphisms in the arrow category. Yeah, you will see that interplay over here. Okay, so now where is this diagram, this dj? Look at that. Where is this diagram? I mean, does it look like a diagram at all? Because we have fixed A in the arrow category, it's one fixed parameter. So therefore, the only part that is varying, yeah, this is all happening inside category C. You understand? This is all happening here in category C. So A is one fixed object, and then Gu dj is varying as per variation of j. So let L to U dj, j in object j, okay. So let this be a limit for ud. Do you agree with this? Like UD must have a limit? I made some comment earlier about this A and we will use that later, but just observe that D is a functor from, D is a diagram in A arrow G. If you further compose it with the arrow category, with the forgetful functor U, then you will get a functor UD. And UD will be a diagram of shape J in category D. And what is the first part of the statement of this lemma? That D has limits of shape J. Okay, so therefore, let this be a limit. And the second part says that, second hypothesis says that G preserves limits of shape J. Yeah, then GL to GU dj is a limit for which diagram now? GUD, very good. Yeah, this is again just by the hypothesis. Okay, so now let's write down the observation that I made earlier. Note that A to GU dj, what is this morphism? This is Fj, yeah, where J is in objects of J, is a cone over GUD. Do you agree with that? How do you verify that something is a cone? It has to commute for every morphism in the base category, in the shape category. Then you will take Fj1 and Fj2 and then GUD alpha. Yeah, that diagram should commute. But that's already taken care of by the fact which is here. I'm just going to highlight it, that this is a by this and this, like this is actually a diagram. Yes.
What is F sub j? What are these?
F sub j is here, it's here. F sub j is a map, is a morphism from A to GU dj in category C. We always have that. Yeah, I mean it's an object, B comma F. You remember, for the arrow category. Yeah, so these two red underlines, do they convince you that this is actually a cone? There was a diagram originally, like we wrote dj for this. Well, you should verify that. Yes.
How does DJ send things to objects? But what about morphisms?
Yeah, morphisms, you can also write them down, but that it's given to be a diagram. Yeah, the first red underline, it says that D is a diagram from J to A arrow G. So therefore, whatever happens in the domain category of J, like for every morphism alpha from J1 to J2, the appropriate thing, like it should get mapped to a morphism in the arrow category. But a morphism in the arrow category already means it's a morphism in category C, which commutes well with respect to the maps from A, which means Fj's. So therefore, just from this red underline, yeah, that's what I said. Like this proof is all about understanding morphisms in the arrow category as cones. I mean diagrams in the arrow category as cones in the base category. Okay, so this is a cone. And now what do we know? Look at the penultimate line. It says that GL to GU dj, where the morphisms are G lambda j, that is a limit cone. And this is any arbitrary cone. So what do we get now? Yes, so therefore we get a morphism. Yes, therefore we get A to what? GL, okay. Let's call it F. Unique, yeah, I mean unique A to GL morphism such that what happens? Well, G lambda J, maybe I should just draw the diagram, yeah. A, then we have GL, and then you have GU DJ. Yeah, this is any arbitrary cone, this is Fj, then this is G lambda J, and this is F, such that this triangle commutes. Okay, so that's the unique morphism which makes this diagram commute. Okay, so what do we get? How can you interpret this single morphism F from A to GL as a single object of the arrow category? Do you understand that? This morphism will give you an object of the arrow category. Yeah, so therefore what do we have? That L comma F, yes, and then to what? L comma F to UDJ. We don't write G over here. UDJ comma FJ is a morphism in the arrow category. A suddenly disappears from the entire picture. Yeah, this diagram commutes means that this happens. What is the morphism? It's lambda J. Okay. So now we have, what did we conclude? So is a morphism in arrow G for each J in objects of J. Okay. So therefore, such morphisms form a cone over D. Just D. Yeah, UDJ comma FJ is actually DJ. So it's just a single object. So therefore it forms a cone over D. And well, now I think you understood the idea how the interplay between cones and morphisms work. So therefore I will leave it as an exercise to verify. Yeah, it's easy to verify. We have seen such proofs multiple times by now, that this cone is indeed a limit cone. And that's the end of the proof. Okay, so we found a cone, and then you have to start with an arbitrary cone, then you again have to go down to category D by applying forgetful functor and play the same game. Yeah. So arrow categories are not as difficult as they seem. Yeah, they are very useful tools to understand this. Okay, so this lemma lies at the heart of the proof, because now we are done with the proof of the first primeval adjoint functor theorem. Are you convinced? Let me show you. Okay, what do we want to show? That suppose it preserves all limits which exist, then it has a left adjoint. Yeah, G preserves all limits. When do we say that something has a left adjoint? If the arrow category A arrow G has initial object for each arrow category, right? So when will that arrow category have an initial object? I mean arrow category, suppose this curly A in lemma 1 is the arrow category, when will it have an initial object? If and only if the diagram, the identity diagram on the arrow category has a limit. Okay, so identity diagram, what is the shape of the identity diagram? Well, let's call it J. Now substitute that J in lemma 2. Okay, and it's not necessarily small, yeah, preserves limits of shape J, so let J be equal to the arrow category itself. So the identity map has limits, yeah, I mean has a limit, identity functor has a limit if and only if there is an initial object. So now you are done by the earlier lemma that I showed, our earlier statement. Okay, so this is the proof. However, I mean this is the first idea that arose in history for adjoint functor theorem, but this is practically useless because nobody is going to check whether there exists a limit of shape which is not even a set. Okay, so we want to understand sets, and for that now I am going to take an example. Yeah, I want to motivate motivation for GAFT. GAFT is general adjoint functor theorem. So general and spatial, yeah, I think the motivation was taken from Einstein. Okay, so motivation for GAFT. Okay, so consider the forgetful functor from groups to sets. Okay, now this functor, does it have a left adjoint? Yes, what is it? Free functor, free group functor, very good. But let us assume that we don't know. Yeah, we want to construct it, so we don't know. Okay, so here I want to point your attention to certain properties. Yeah, note that the category of groups here is complete. Okay, complete as in it has got all small limits. Then it is locally small because home sets are just sets. Yeah, so these two properties are true, and moreover for any set X and group G, the morphism from X, any morphism, yeah, I mean I shouldn't say the morphism, any morphism from X to the underlying set of the group G factors through UG prime, where G prime is a subgroup of G generated by, I mean if I am calling it F, then F of X. Do you agree with this? That any function from X to UG, however large the group may be, this particular set function is always going to factor through one particular smaller subgroup, comparatively smaller subgroup. Moreover, yeah, I mean this is important, like where what is the cardinality of this group generated by f of x, of subgroup generated by f of x.
Cardinality of f.
Don't say omega, aleph naught. So it's maximum. I mean, I can just say aleph naught plus or maximum. Plus is just maximum. Cardinality of x itself. Okay. So aleph naught plus cardinality of x, if you don't know cardinal arithmetic, we are just taking maximum of two cardinal numbers and we are, let's say, assuming axiom of choice, so any two cardinal numbers are comparable. Yeah, so cardinality of x is a fixed quantity. So this aleph naught plus cardinality of x is also going to be a fixed quantity. Now the question is, how many groups are there up to isomorphism of this cardinality? Let me ask you a simpler question. How many finite groups are there up to isomorphism? Well, you choose one finite set, then you choose one binary operation on that. A binary operation is nothing but a subset of G cross G cross G, because it's a binary operation. Now, whether it satisfies properties of being a binary function, whether it has an inverse or not, that's irrelevant. But it's still a set. Yeah, so one choice of a set together with one ternary operation. That's all you need. Okay, so when you take union over all finite subsets, finite sets, and this pair, yeah, that a finite set G comma a ternary relation on G, then that is still a set. Very good. That's the important point here, that is still a set. The similar argument will show you that for any cardinal number kappa, there is only a set of groups of maximum that cardinality up to isomorphism. Okay, so let me write that down. But there are, but for any cardinal kappa, there are up to isomorphism only a set of groups of cardinality kappa. Cardinality even less equal kappa. You agree with this? I mean, you can do it with any algebraic category actually, right? Like even if I replace groups with abelian groups, modules, it doesn't matter. You just have to close it under certain operations. Okay, so are you convinced with this? Yeah, that up to a certain cardinality, there is only a set of groups up to isomorphism. Okay, so basically this property is extremely important. Yeah, what does this property say? That you can always factor through a group which is of a specific cardinality, which cannot exceed a specific cardinality. Any set function will always factor through one such thing. So basically, now what we are saying, that there is only a set of options of morphisms through which every single morphism from X to UG will factor. You understand this whole process? Yeah? So this is what we want to capture. Yeah, this is called the solution set condition. The solution set condition says that there is a set of morphisms in your category through which any morphism from that specific domain will factor. So you don't need to worry about proper classes. Yeah, and that is where it makes it possible to verify this. Okay, the primeval adjoint functor theorem said that we have to talk about even large categories at some point, large shapes of diagrams. But here we are avoiding that by requiring something simpler. Okay, so now I can state what is GAFT. So general adjoint functor theorem. Which we usually write at GAFT. This theorem was originally proved by Peter Fried. It's interesting to check out the Wikipedia page for Peter Fried. Okay. Fried has proved many results, like fundamental results in category theory. Okay. So suppose D is locally small and complete, and see that I'm just following the blue letters. Yeah, it's locally small and complete, and G from D to C preserves all limits, means it's continuous. Yeah, G is continuous. Then G preserves, then G has a left adjoint. If and only if it satisfies the solution set condition. Okay, now I have to state what is the solution set condition. It's simple to state. For any A, now where is A coming from? Object of C. For any A, there is a set. See, normally I write round brackets, yeah? But here I am going to write curly brackets because I want to denote it's a set. Yeah, so Bi Fi I in I of objects of the arrow category such that for any other object of the arrow category, there is some I in I and G from Bi to B such that Bi Fi to Bf, this G is a morphism in the arrow category. Like, I will write a simpler version. In other words, the home set in the arrow category from Bi Fi to Bf is non-empty for some I. Do you understand what I am saying? that every single morphism from A to some other thing in like GB, yeah, so that must factor through one of the FIs. Yeah, I mean, maybe I should draw this diagram to help you what I'm trying to say here. This is the diagram. Yeah, A is sitting here, then you are given some B comma F, which means some morphism F from A to GB, that is given to you. Then what we are saying is that there will exist some BI from this set collection, set index collection, such that this particular triangle will commute. So any morphism from A to GB will factor through a morphism from A to GBI. Okay, now here you have to notice certain things. I mean, the proof itself will make those things clear. Yeah, where we are. So I want everybody to pay attention to whether or not we are using every single hypothesis. Yeah. So let's do the proof. Now one side is very simple. Can you tell me how? Like suppose G has a left adjoint, then why will it satisfy the solution set condition? Image of GA. GA doesn't exist. A is an object in C. So GA doesn't make sense.
Like GFA.
GFA. So what is the morphism from A to GFA?
The unit.
Yes, unit. The eighth component of the unit. Okay. So if F is a left adjoint of G, then FA comma eta A, yeah, this is a solution set. Okay. Yeah, this is easy to write down, but are you convinced? Let's see, I will write something more for your help. See, this is eta A, then this is GFA, and this is given to be GB. Do you remember from our last lecture what this corresponding map is from GFA to GB? G suffix E, G eta. No, G eta will make it, G eta doesn't even make sense here. Eta can only be applied to objects in C. But this diagram will commute provided you can put something here, yeah? Let's say that morphism is GG. This diagram will commute if and only if some other diagram commutes. What is that diagram? That diagram is simply FA to FA, which is identity, because under adjunction, unit corresponds to identity. And then whatever this morphism is, that has to be and GG. Well, this diagram will commute. But in one of the proofs, we actually saw how to construct this G. What was G? From FA to B. The only thing that we can do, yeah? G is, yes, from FA you can only go up. Yeah, ultimately we want to come back to B. Yeah, so this is the composition. I will write this composition. We want to come back to B, this composition. So it must be via FGB. And FGB to B we always have the co-unit epsilon B. And this map FA to FGB, well, we have that FF. So this is the only G that will work. This G will correspond to F under the adjunction, and that G will make this diagram commute. So therefore this is the singleton solution set. Understood this part? You just have to remember what we did in that proof. Yeah, this is, we defined some capital phi and capital psi. Maybe I can fetch it for you. Yes, it's here, I think. Yeah. You can see psi of f is ff and then followed by epsilon b. This is what we did in the proof for triangular identities over here. So we are just using that. Yeah. So one side is obvious. Now we are trying to prove the second side, which is the main proof of this theorem. Obviously, we never wanted one side. Yeah, one side was obvious. Okay. By lemma 2, yeah, what do we get? A arrow G is complete. Do you agree? A arrow G is complete. Let me show you lemma 2. See, lemma 2 says that if D has limits of shape J and G preserves, then A arrow G also has limits of shape J. But in the statement for our GAFD, we have said that D is D is complete and G preserves all limits. So therefore, A arrow G has all limits. So it is complete. Okay. So we have used this. And is locally small. Since D is. Yeah, because all morphisms in the arrow category, they are actually morphisms in D which commute. Yeah, appropriately. Okay. So, now what do we need to show? That the arrow category, now arrow category is any, yeah. This is for happening for any A which is object of C. For the arrow category, we just have to show that it has an initial object. That's our goal. Yeah, and we are going to use the solution set condition to construct such an initial object. Okay. So for the ease of notation, let us assume, now this point onwards we are changing the notation altogether, that A is a complete locally small category with a solution set AJ, J in J. Okay, so this is what we want. Okay, so what is the meaning of being a solution set in this category? It means that for any given object of category A, there is at least one morphism from one of the AIs. The home set in A is non-empty. Can you see that this is actually a weaker notion of initial object itself? Yeah, we are not asking for uniqueness, but we are asking for existence over here. That all the objects together, yeah, they will have at least one morphism to any given object. We can also combine the data of all such more objects into one single object by taking a product, because then from that product we can drop down to one of the components by a projection map, and then from that A you will have a non-empty home set. So that the entire home set is non-empty. Well, let's do that exactly. So let P be the product object, so that the home set from P to B is non-empty for each B in objects of A. Okay, so this product is a my T object. Yes.
Definition of a solution set.
Uh-huh.
The solution set. There is a solution set for every object of A.
There is a solution set for every object of A, but that means for the arrow category A arrow G, the solution set simply means that this is weakly initial. This whole set is weakly initial. Yeah. So we are asking for that, but we are asking for a set which we can combine into a one single object. Yeah. So let's start with that. Okay. So what do we need to show? It's a very beautiful piece of proof. Yeah. We need to show that A has an initial object. Okay, so now we have to construct a diagram, and we will construct a limit for that diagram. And this process is quite similar to how we constructed, do you remember in one proof we constructed a massive product, two massive products, and then one equalizer. Now we are going to do the same thing, but we are only going to use one massive product and a very complex equalizer. Okay, so consider the diagram P to P, where the arrows are endomorphisms of P. Can you see that now here we are using that the category is locally small? Yeah, this is still a set. So therefore this is a small diagram. Let its limit be I, and I'm just going to call it I. Okay. So this is an equalizer. Yeah, it's an equalizer not of a pair but of lots of morphisms. Now, do you agree with me that this equalizer is going to be a monomorphism? Okay, so let its limit be this. And do you remember the proof that all equalizers are monomorphisms? Yes. So similarly, this one will also be a monomorphism, because if you have two morphisms with target I such that I composed with F is equal to I composed with G, then you go through this diagram, and then that will be that will give you two different factorizations through the limit cone, and well, uniqueness of limit will give you, yeah. So clearly little I is monic. Okay, now we have to use this, that this is monic. Okay, now since the home set from P to B is non-empty for each B. We also have home set from I to B is non-empty for each B. Do you agree? Because we can go from I to P via little I and then from P to B. So therefore, out of two properties for an initial object, we have shown one. One is existence and another one is uniqueness. So now we are going to show uniqueness. Okay. So suppose I to B, we have got two morphisms. Is a diagram. Well, whenever you see this diagram, two morphisms, what do? You construct equalizer. Okay. With equalizer, this, and let me call this E, and this is also mono, yeah, because it's an equalizer, it's a monomorphism. Okay. Okay, now since home P comma B is non-empty for each B, in particular home P comma E is non-empty. So let P to E H be any morphism. Okay. Now see what we have got. Then we have this P, you can go to E via H, then from here you can go to I via E, and from I back to P we have got I. Okay? This one you can see? Yeah, I just wrote down all the things. So basically IEH is an endomorphism of P. And there is another endomorphism, by the way. What is that? Identity, very good. Okay. Then what do we have? Like this is little I over here. Okay. Then these compositions are equal. Then we have that IEHI is equal to 1 PI, which is equal to I composed with one identity capital I. And since I is monic, what do we get? We get EHI is equal to 1 sub I. What does this mean? Well, this E that we obtained here, yeah, before that E, if I put HI, then I will get identity. It is both monic and split epi, correct. Therefore, well, we don't even need that, we just need it's a split epi. Yeah, therefore E is a split epi, and hence, yes, therefore we cannot have two different morphisms and we are done. So we have shown that capital I is indeed an initial object in the category. Yeah, very beautiful diagram chasing proof, and it's not hard. Any questions here? Oh, because home from P to B is non-empty, so there is a morphism from P to any object. Okay, so now see that we have use this solution set condition to get this, and therefore by this solution set condition satisfaction property, GAFT will guarantee existence of the free group functor. In fact, it will guarantee existence of free algebra functor for any algebra. Yeah, you just need to close it under finitary operations, and the same argument works. Yeah, you have to take the algebra sub-algebra generated by the image. That's all, and its cardinality won't grow drastically. Very sleek proof. Yeah, and there is one more thing which, I mean, just for the sake of completeness, I will do one more example. So another non-example now. Okay, so this is C-lat is the category of complete lattices. You understand complete lattices? Like every subset has a supremum and every subset has an infimum. So in particular, they are bounded, yeah, because bounds are also entire suprema and entire infima. Okay. So now consider this particular functor. Every complete lattice is itself a set to begin with. If you don't know what complete lattice is, think about the power set of any set. That's a complete lattice. Arbitrary unions exist and arbitrary intersections exist. Okay. So if A is a set with 3 elements and kappa is a cardinal, then in 1964, A.W. Hales showed that for any showed that the solution set condition fails for A and any kappa. A and kappa, I mean, that's the given thing. So what does this mean? That if you are given one lattice, yeah, like let L be a complete lattice, then what I'm saying, like let's call this U again. Basically I'm saying this: if you are given a function from A to UL, any function, then what was our argument earlier? That we have to generate a sub-algebra, yeah, sub-algebra of L by the image. But here the image is just 3 elements, yeah. A is a set with 3 elements. He showed that the solution set condition fails, which means he showed that for any cardinality kappa, there is a lattice which is generated by 3 element sublattice. For any lattice L of cardinality at least kappa, there is a sublattice generated by at least 3 elements which has cardinality bigger equal kappa. So the solution set condition fails here. The point of this particular non-example is to show that the solution set condition actually works in those simple examples. The algebra, yeah, algebra to sets, the forgetful functors, is because all the operations are finitary. Here, when we talk about a complete lattice, then the operations are not finitary. Yeah, complete means supremum over any subset, and then the situation goes out of hand. Right? I'm not even going to keep this. You just figure out what this means for yourself. Complete lattices is a very different story. Yeah, it doesn't fit into the algebra. Whereas if you had lattices and sets, forgetful functor, then again the argument will work. Okay? Fine. Let's stop.